So we have been looking at the anti-Markovnikov radical addition of HBr to alkenes and also to alkynes, and we have seen that this reaction is spontaneous and readily applicable to HBr and not to HCl and HI. And the reason is because of the fact that the delta G for HCl and HI are all positive. And if we look at this following slides, we can see why the addition of HCl to double bonds is not applicable, it's not feasible. In the first propagation step, you can see here that the reaction has negative enthalpies for HCl and HBr, but it has a positive enthalpy change for HI. The entropy is positive for all of the reactions, and that's because it's an addition. You are going from 2 units or reactants to 1, and so delta S will always be negative on the decrease. So negative times negative becomes positive. See, so the only way this reaction can happen is by making sure that the enthalpy change stays negative. Now, the question we can ask is, will the entropy change favor the products or the reactants? Of course, it's going to favor the reactants because the entropy change, as you can see, is possible. It's positive. The enthalpy change is affected most by the relative stability of the radicals. For instance, if you look at the first propagation step, in the case of both reactions, you are forming a tertiary radical. You see, you are forming a tertiary radical. So the enthalpy change for both HCl and HBr is negative. Of course, for HI is positive. That's because the HI radical the I radical is way more stable than the tertiary radical. So the HI reaction will never favor products, and that's because both delta H and negative T delta S are positive. So how can the temperature be adjusted to favor products? You have to ensure that the temperature is always low, because if the temperature is low, then T delta S is insignificant and the reaction is controlled essentially by delta H. Now, for the key to understanding why the addition of HCl to double bonds and triple bonds is not feasible is by looking at the second propagation step of the radical addition. As you can see here, the second propagation step involves a positive delta H for HCl, but a negative delta H for HBr. You see? And as a result, what happens is the reaction overall is not favored for HCl. See, for the second propagation step, why is the entropy term 0? Of course, the entropy term is 0 because you can see there is no change in the number of reactants nor products, and so the entropy change is 0. You began with 2 molecules and you're ending up with 2 molecules. So what small differences in entropy between products and reactants might account for entropy changes being slightly negative or positive? Of course, the entropy change can be slightly positive or negative if there are slight changes in the degree of freedom. See, that's the only thing that will contribute to a negative or positive change in entropy. See, We see that for the HCl, the second propagation step will not be product favored. We see that already. It's not for the product favored because delta H is greater than 0. HBr is the only reactant that favors product formation for both propagation steps, and that's because in both propagation steps, delta G is less than 0. So that explains why the addition of HBr to a pi bond is favored for HBr and not for HCl. Now, we might ask ourselves the questions: might the overall propagation involving HCl be product favored if the delta G step 1 outweighs the negative delta G step 1 outweighs the positive delta G step 2? Of course, yes, it will, because if you add up both delta G's, what's going to happen is that you're going to still have a negative delta G, which will make the reaction spontaneous. Now, addition reactions often form a new chirality center. See, as you can see here, because remember we went through a radical, see, and that radical will lead to racemization. The formation of that radical will lead to racemization. Recall that at least one reagent in a reaction must be chiral for the reaction to be stereoselective. That's something we learned a while back. So if we're going to predict the product distribution for the reaction below, we can see that we're going to have racemization. We're going to have racemization. We're going to have racemization. See, we're going to have racemization in 50-50. Now, in chapter 9, we learned how some. So let's look at radical polymerizations. Let's look at radical polymerizations. Before we go on, I just want to say some things that we need to know about radical polymerizations. Okay, and that is the fact that polymerization of ethylene via a radical process generally involves chain branching, and when vinyl chloride is polymerized, we get polymervinyl chloride. Now, we know that polymerizations can go through an ionic pathway, but here we're talking about the free radical pathway because it's frequently used. For instance, you can polymerize ethene or ethylene to get polyethylene. See, you can do that. And the reaction again proceeds via a radical mechanism in which you have an initiation, right? One, you have the formation of the initiators, which will be the alkyl peroxy radicals. Then what happens is the initiator can now promote the polymerization of the individual ethylene monomers, and the propagation step continues, right, until it is terminated by coupling from another radical or from another alkyl radical. So the radical polymerizations generally produce chains of monomers with a wide distribution of lengths, and we can actually control the length of the chains by sometimes you can introduce free radical inhibitors. However, because we are dealing with a primary radical here, it's not always easy. It's not always easy. And so in chapter 27, if we ever get there, we will talk about specialized catalysts that can be used to control polymerization reactions. These are specialized catalysts. Branching is common in some radical polymerizations, very, very common, right? And branching makes for more flexible polymers, such as squeeze bottles. Okay, when the catalyst is used to minimize branching, more rigid materials are produced, such as squeeze bottle caps. You know, and of course we know that the branching will affect the degrees of freedom, right? And so that's why it's going to be more flexible. It's going to be more flexible because it will increase the degrees of freedom. Now, many derivatives of ethylene are also polymerized. These are just some different grades of ethylene, of polymers that you need to know about. We have polyethylene, which is grade 1. We have polyethylene, which is grade 1. We have high density polyethylene, grade 2. We have polyethylene chloride, grade 3. We have low density polyethylene. We have polypropylene, PP, that's grade 5. And we have polystyrene, that's grade 6. These are just some classes, some different grades which you need to be aware of. And also we have Teflon, which is used for non-stick coating for frying pans. Now, radical polymerization process is a process that involves cracking, right? And the cracking and reforming processes. And we remember that crude oil is cracked to produce smaller alkanes and alkanes, you see, and reforming increases the branching. These are things that you need to know. Okay. And so we have looked at the synthetic utility of halogenations, and we have seen that bromination is way more selective than chlorination. Okay, and that's because the rate determining step in the case of bromination is endothermic, and there's a very, very large difference in the activation energy for the formation of the tertiary radical compared to the secondary radical, and that's why the reaction goes exclusively through the tertiary radicals. In fact, you could get 100% of tertiary radicals and 0% of primary radical formed. The temperature can be used to help avoid polysubstitution, and that's because higher temperatures satisfies all the activation energy requirements, making all pathways to polysubstitution feasible. When you have higher temperatures, that means you have enough energy for all reactions, irrespective of the magnitude of the activation energies, to happen. You see, but once the temperature is reduced, then the reaction has no choice but to go through the pathway in which a minimum activation energy is required. Chlorination can be useful with highly symmetrical substrates, especially substrates where you have only one type of hydrogen, right? And the other thing you have to remember is it's difficult to avoid polysubstitution because both propagation steps are exothermic. You see, that's the case of chlorination. So chlorination is difficult to control because the activation energy for the formation of the primary, secondary, and the tertiary radicals are pretty close. However, with bromination, right, the activation energy for the formation of the primary and secondary radical is much, much, much greater than the activation energy for the formation of the tertiary radical. In fact, the activation energy for the formation of the tertiary radical is so small that the reaction goes exclusively through the tertiary radical formation and very little of the secondary, if any. Not a lot, not a lot. So these are just some, this is just to summarize halogenation reactions. Recall that you can use NBS to carry out a bromination, right? And that once you get the brominated alkane, then you can carry out an elimination and you can form your alkane. So a great way to put a handle on an alkane which is pretty much unreactive is by making it undergo a bromination. Once you are able to introduce the bromine, which is a great leaving group, then you can make a double bond and you can do all kinds of interesting chemistry afterwards, as you can see here. We have some other addition reactions which I would like to, but I want you to note this very, very much. Note this because you can do substitution reactions on alkanes, and once you have the substituted product or the bromo alkane, then you can carry out an elimination to form the corresponding alkene, and then you can do all kinds of interesting chemistry with it. So we have seen that the synthetic utility of halogenation is better with bromination because it's more selective why chlorination is not as selective. It leads to polychlorinated products.